So welcome to lesson 3.8, which is time series analysis. Now, a common situation we'll have in theoretical history is that we've got some data that is varying over time t. So this might be, for example, the amount of war in the world system, or it might be real wages, people's earning power over time, or it might be the area of an empire changing over time. So this is a time series, and what we want to do is look for some kind of pattern in this data, and that is time series analysis. And in time series analysis, this kind of chart is sometimes called a signal, or this is the signal that we're analysing, or also the waveform. So those are words we might use. And of course, what we've actually got, this is just a picture, but we've got numerical data behind this. So we've got a set of values of times and the values of whatever it is we're looking at, the amount of war or wages, whatever. So we've got these points, time t2, value 2, t3, v3, and so on. So this will be a set of numbers in an Excel spreadsheet or something like that. And what we want to do is some number crunching on this to try and bring out the patterns in the data. And when we're talking about patterns, we're typically interested in some kind of regularity to our signal or waveform. So we're looking for some kind of cycles in the data. And we might expect that there are typically many cycles, or at least several cycles, that are superimposed on each other, overlapping. So it's not really obvious what they are because they're interfering with each other. So time series analysis is about extracting those superimposed cycles from this confusing data of many things overlapping. And we're going to be considering three different ways of approaching that. So the first one is Fourier analysis. And this is about decomposing our signal into a set of sinusoidal oscillations or sinusoidal cycles. So we know what a sine looks like. So it's a very regular, smooth oscillation with a particular pattern to it. And we're trying to see the extent to which there are sine cycles like that in our data. And what we're really interested in is the periods of the cycles, how frequently they repeat, or the frequencies of the cycles. So we're trying to find a set of frequencies of the cycles that are implied within this waveform or signal. And then the second approach we'll be considering is that of wavelet analysis. So in this case, it's useful when the frequency is changing over time. Or the frequencies change over time. So in this case, it looks as though we've got a rapid oscillation. It's going up and down quite rapidly. There's also a kind of longer up and down motion. But then here it disappears. So it looks as though that longer frequency, lower frequency oscillation is present there, but then it disappears here, and then maybe it comes back here beyond. So with Fourier analysis, we just look at the overall picture. We treat the thing as a whole and look for the cycles that might be in it. But with wavelets, we kind of move along and we look at what frequencies are present at different parts of the signal. So we get a changing picture of the frequencies that are present in our signal. That's wavelets. And the last thing we'll look at is autoregression. And this is about finding the times or the timescales over which our signal repeats, but not necessarily assuming that it's a sine wave. It could be any kind of pattern, but it repeats after a certain amount of time. So in this case, we might say there's a pattern here of a sort of peak followed by another peak, and that repeats. And then it doesn't seem to repeat here, but it repeats there. But it might, with autoregression, we might pick up that it in fact is repeating here, but it's just that for some reason the peaks are much smaller at that point. But we would still pick that up because we're still finding two peaks together and two peaks together. Obviously, the autoregression would be stronger if this were, looked exactly like that, but autoregression will still pick up that those peaks are kind of in the right place. But anyway, with autoregression, we're looking at arbitrary shapes, but how they repeat over time, if there is some kind of regularity in the way they repeat over time. And we'll start with Fourier analysis. Okay, so Fourier analysis. What I've drawn here is two sine waves, one with a frequency of omega, or an angular frequency of omega, and one with an angular frequency of 2 omega. So this is like sine omega t or sine 2 pi omega t. So this has double the frequency of that and also half the amplitude. And what I've shown below is what happens when we add these two sine waves together. We get this kind of shape. It goes up to a peak and then it's kind of flat here where it crosses the axis, and then it goes down to a peak, comes back up to another peak, and then it repeats. So we can see why that happens here, that as if we start here, the two sine waves are going in the same direction. So this one is reinforcing that one, so it sort of pushes the peak up. But here, this 2 omega sine wave is crossing the axis in the upward direction, when the longer period omega sine wave is crossing the axis in the downward direction. So they're kind of cancelling out. So this is why it's 0 for a while around here, pretty much. It's just flat. And then as they come down here, again, this starts to reinforce that one, so it amplifies that peak. And here they're swinging together this time as they go through the axis from below. And then after that, it's just the same thing over again. So if we looked at that, we wouldn't necessarily see straight away that it's composed of those two sine waves. But Fourier analysis is about taking something like this and working out what it is composed of. In this case, a sine wave and another sine wave of half the amplitude and twice the frequency. And the magic of Fourier analysis is that by suitably adding up sine waves, we can get any kind of arbitrary waveform or arbitrary signal. So any waveform can be broken down into some suitable combination of sine waves. And to give another example of that, we can take a square wave that looks like that, and if we start with a sine wave, that doesn't look very much like a square wave, but we'll say that is amplitude 1 and frequency 1. So let's say, in fact I'll put it another way, let's say that's just sine t. It's sort of a bit like a square wave, but you know, not very square. But if we add to this 1/3 sine of 3t, we get something that looks more like that. I've gone a bit wonky, but this is sine t plus 1/3 sine 3t. And this looks more like our square wave. Obviously it's got some fluctuations here, it's not completely flat, and also these aren't completely vertical. But we can continue this process by adding sine t plus 1/3 sine 3t plus then 1/5 sine 5t, 1/7 sine 7t, and so on. And the more terms we add, the closer this gets to a square wave. And if we continue this to infinity, we would get exactly a square wave. So repeats the point that we can take any arbitrary waveform and it can be decomposed into some combination of sine waves. So what we're saying is that if we've got some time series in a variable x, the amount of war, real wages, whatever, that depends on time, we want to understand that as the sum of a set of sinusoidal oscillations. N omega t is the frequencies, where n varies from 1 or even 0, in fact, up to potentially infinity, and they will have different amplitudes, so A, N. And we're saying that any signal can be represented by such a sum of sine waves. And in fact, we could also have cosine waves as well, properly speaking, but you know, that just will complicate it. Just to understand the principle, we'll just focus on the sine waves. And so in this case that we looked at here, we've got A1 is 1, let's say. When n is 1, we've got sine omega t, so A1 is the amplitude. That will just take that to be 1. And then for 2, when n is 2, the amplitude A2 would be a half. I said that this sine wave was a half the height of that one. So this signal can be represented as a sum of sine waves with the amplitudes 1 when n is 1 and a half when n is 2. And then for n is 3, 4, 5, the amplitudes are 0, because those, you know, it's just those two added together. Whereas for our square wave, we had if we take A1 as 1, A2 0, because that wasn't involved, there was no sine 2 omega t term. A3, though, we said was a third when we've got 3 omega t. A4 is 0, A5 is 1/5, and so on. So our goal is to take some arbitrary time series and work out what these amplitudes are, the AN. That's what we're interested in for all the different values of n in the possible sines that we're adding together. So let's have a look further at that. Now, in reality, you would just use a computer program like R or something to do the Fourier analysis for you and spit out the amplitudes. But I'm just going to go through a bit the principle behind that, so that it's, you know, not a complete mystery, and you have some understanding of what's going on. So we use the facts. The integral of two sines of different frequencies multiplied together, so sine m omega t times sine n omega t dt, between minus pi and pi. I'll put a 1 over pi in front of that. So the integral from minus pi to pi of this was two different sine waves is 0 if m is not equal to n. Doesn't matter what they are, but if they're not equal, the sine that integral comes to 0. It's only when m and n are equal that this has a value of 1. If m equals n, that's if I didn't put the pi 1 over pi in front, it would be pi. So I put the 1 over pi in front, so it equals 1. And this is because you know, sine waves tend to be above and below the axis, so that that on average they're 0. And then if you compare them with anything, on average they will be 0. But it's only if they're it's exactly the same that they'll always swing together, and so they won't, when multiplied, come to 0. So we can use this then, that if we take this integral, so if we take this integral 1 over pi minus pi to pi of our expression for xt up here, an sine n omega t, times sine of m omega t, this will be equal to am. Because for all the values of n in here, when we multiply it by sine m omega t, they will all give 0, except in the one case when m equals n. And then it will be an times sine m omega t from here times sine m omega t from there. So it will just pick out that particular value. Because we're integrating it with sine of m omega t, we'll get am. And so that means then that if we take our signal, which is x of t, and put that in here, because this, we're assuming that x of t is this sum of sines here, x of t, and multiply that by sine m omega t, integrate dt, then we'll get exactly the same am, because you know, x of t we're assuming is this sum of sines, and it's only the sine of frequency m omega t that will come out of it. So we will get the amplitude of the sine m omega t part of x of t. And so that is what we're interested in. We're interested in these values, am or an, whichever subscript we're using, for our signal. So that if we put into this equation, if x of t were this, and we integrated this, the values of this multiplied by sine omega t and sine 2 omega t, we would get out, firstly for sine omega t it would come to 1, and then for the sine 2 omega t it would come to a half. That would be a1 and a2, and then for anything else it would be 0, because we said that all the other coefficients are 0. And then similarly for the sine wave, if we did this, the square wave, if we put the values of the square wave in here, so they would be, you know, like 1, 1, 1, 1 while it's at the top, and then they would switch to -1, -1 at the bottom. If we put our values for the square wave, our formula for the square wave in here, integrated it, we would get a1 would come out as 1, a2 would come out as 0, a3 would come out as a third, a5 would come out as a fifth, and so on. So, as I say, it's not something we would actually do manually. We would have a computer program to do it for us. But that is the principle behind it. That's what the computer program is doing. It's doing this integration to pick out these amplitudes. And so what you will get out is a set of values, you know, for a1, a2, a3, etc. So as I say, it would be 1, let's say for our square wave it would be 1, 0, a third, 0, a fifth, and so on. And in general for a signal we would have you know, all sorts of values here for a2 and a4 and so on would all be filled in. So we'd find these values of the strength of each sine wave in the signal. And now we don't normally work with the amplitudes per se, because the amplitude could be negative if it's the sine is there but it's swinging kind of in the opposite direction. So what we take is the squares of the thing, a2 squared, a3 squared. That will be the numbers that come out. So it would be 1/9, 1/25, and so on. And then what typically a computer program for doing a Fourier analysis will give you is these sets of numbers, a squared, and to visualize it, you'll plot it on a chart. So along here is omega, the frequency. Perhaps I could just put F for frequency rather than omega as I was using earlier. F for the frequency, and here is the strength, or we could call it. When we square, if it's in a physical situation where it's a radio wave that contains different frequencies, the square of the amplitude corresponds to the amount of power in the signal at that frequency. So this is the power, you could say, the power in the signal, or the power density. It's how the power is varying with frequency. So for our square wave, we found that if we put the frequencies along here, 1, 2, 3, 4, 5, etc. For the square wave, we found, well, if the amplitude 1, so that 1 squared is 1, that 2 it's 0, and here 0 it's 0. At 3 it was a third, so that which comes to a 9th, and a 25th, and a 49th. So we'll get something looking like that, just having peaks at the odd numbers there and decreasing as we go to higher and higher frequencies. So this chart then shows us for our square wave what the frequencies present in that square wave are. And there's this big peak at 1, because that's the basic frequency of our cycle. it's oscillating at this rate, the basic frequency of the square wave. And yes, there are some small frequencies superimposed on that, but they are pretty small adjustments to it to make it exactly fit these square corners. But the basic frequency in there is that one, and that's what we're seeing, this strong peak at that frequency of 1. And now let's look at a practical, real example of that. Okay, what I've drawn up here is an example from a work by Peter Turchin on the disturbances in ancient Rome from about 600 BC to AD 600, and he's using some data prepared by Peter and Sorokin. And I haven't drawn it accurately, I've just drawn it sort of rather stylized to bring out the points here. So what we can see is that the number of disturbances per decade or whatever it is in Rome fluctuates up and down, and there seem to be some peaks here around about 100 BC and around about AD 250, and also going further back around 450 BC. So this is our time series, this is our signal, this is our waveform, and we want to do a Fourier analysis of this to pick out the frequencies in this fluctuating incidence of disturbances. And here it is. So now we've got the frequency plotted along here, and up here is the strength of the signal at each frequency. So I've labelled that the spectral density. So this is sometimes called the spectrum, or the power spectrum of this signal. The spectrum is a breakdown by frequency, showing the strength of the signal at each frequency. That's the spectrum. And what we find is that there are two basic peaks. The frequency here is about 0.3, so this corresponds to a cycle with a period, Turchin finds, of about 340 years. The frequency, I should have said, is per century. So that's 1 disturbance per century, that's 2 disturbances per century. This is 0.3 disturbances per century, which is, in other words, 1 over 0.3, or 3.4 centuries, which is 340 years. And then here is another peak with a frequency of 2 per century. So 2 per century, that's a period of every 50 years. And Turchin finds that these accord with his own, theories of social unrest. That firstly there is this long period cycle that's to do with population expansion causing poverty because there's too many people for what the available resources can support, leading to social unrest, which causes population to decline, collapse, leading to more peaceful times, but then eventually the population starts to rise again and you get back to poverty and unrest again. And that takes a time of about 340 years. And but he also suggests there are generational cycles, so that if one generation is rather warlike or violence prone, then the next generation is more peaceful, and then when you've had a peaceful generation, the next generation, having grown up in peace, is less kind of inoculated against violence, and so is more prone to conflict again. And so that is our 50-year cycle, the two 25-year generations. And what we can see that really, now we've got that understanding in this chart, that there is the, if I perhaps draw it, there is the 340-year oscillation, and here is the, the 50-year oscillation superimposed on that. So we can kind of see, intuitively where those come from. Now that's, in this case, it's pretty obvious because I've deliberately drawn it that way to pick that out. If you actually look at the original data, this peak isn't so pronounced, and these peaks look more different than I've drawn them here. But nevertheless, it's because you've got these peaks spaced at about 340 years, and you've also got these constant fluctuations up and down in the data on disturbances. So that is an example of Fourier analysis, and we say that this the data here, these show based on exactly the same data. They're just two different ways of looking at the data. One is by plotting the data against time. So we could say that this is showing the data in the time domain. And here we're plotting the data as a function of frequency. So this is said to be the frequency domain. But the point is that they carry the same information, just presented in different ways. And as we can see, the frequency domain is kind of more useful from the perspective of finding the patterns in the data. The time domain paints a pretty picture, but the frequency domain gives us what the regularities in that time signal are.